The A** search algorithm builds on the principles of shortest path algorithm to provide a faster solution when faced with the problem of finding the shortest path between two nodes. It achieves this by introducing a heuristic element to help decide the next node to consider as it moves along the path. Imagine trying to find the shortest route on a map between London and Glasgow. No one with a reasonable grasp of UK geography bother himself to evaluate a route that went via Brighton. The trade-off between speed and accuracy is important. In some applications, accuracy is less important than computational time. For example, in some applications, a route that is calculated in seconds and is short enough is preferable to having to wait 10 minutes for the perfect route. The heuristic function provides an estimate of the minimum cost between a given node and the target node. The algorithm will combine the actual cost from the start node, referred to as Gn, with the estimated cost to the target node, referred to as Hn, and uses the result to select the next node to evaluate. There is no single best heuristic to use in pathfinding, as every application is different. For example, if the cost relates to a distance, it could be estimated by calculating the straight line distance between the nodes, perhaps by using one of the following methods: Euclidean distance, Manhattan distance, Great Circle distance. The Euclidean distance between 2 points is the length of a line between the 2 points. It can be calculated from the Cartesian coordinates of the points. It is nothing but the sum of absolute values of differences in the goals x and y coordinates, and the current point x and y coordinates respectively. Manhattan distance in red, blue and yellow paths all have same shortest path length of 12. In Euclidean geometry, the green line has length of 8.5. In the real world, we can use any of the methods to calculate the heuristic value, but it depends on the moving condition. When we are allowed to move in any directions, Euclidean distance heuristics can be used. When we are allowed to move in 4 directions only, right, left, up, and down, Manhattan distance heuristics can be used. In the upcoming examples, heuristic values would be given as assumptions. The numbers written on edges represent the distance between the nodes. The numbers written on nodes represent the heuristic value. Find the most cost-effective path to reach from start state A to final state J using a asterisk algorithm. Step 1. We start with node A, node B, and node F can be reached from node A asterisk algorithm calculates f, b, and ff. Since ff is less than fb, so it decides to go to node f. Step 2. Node G and node H can be reached from node F. A asterisk algorithm calculates fg and fh. Fg equals 3 plus 1 plus 5 is equal to 9. Fh equals 3 plus 7 plus 3 is equal to 13. Since fg is less than fh, so it decides to go to node G. Step 3. Node E node H in node J can be reached from node I. A asterisk algorithm calculates f, e, f, h, and fj. Fe equals 3 plus 1 plus 3 plus 5 plus 3 is equal to 15. Fh equals 3 plus 1 plus 3 plus 2 plus 3 is equal to 12. Fj equals 3 plus 1 plus 3 plus 3 plus 0 is equal to 10. Since fj is the least one, so it decides to go to node J form node I. Given an initial state of a 8 puzzle problem and final state to be reached. Find the most cost-effective path to reach the final state from initial state using a asterisk algorithm. Consider Gn equals depth of node and Hn equals number of misplaced tiles. As it is apparent, the initial state has 4 misplaced tiles. 1, 2, 6. 8 are misplaced and should move to find their places. For the first move, we have 3 choices. Filling the blank tile by number 6 or 7 or 5. If tile 6 moves down, the heuristic number would be equal to only 3 misplaced tiles. As depth of node is equal to 1, so estimated cost of path in this stage is 1 plus 3 and would be equal to 4. If tile 7 moves right, then we have 5 misplaced tiles, so estimated cost of path in this stage would be equal to 6. If tile 5 moves left, then we have 5 misplaced tiles, so estimated cost of path in this stage would be equal to 6. Among these 3 movements we choose the least estimated cost of path. That would be tile 6 movement toward down. These steps continue until the goal state is achieved.